Mom, today Arthur told me that he thought the Earth was flat.
Eratosthenes must be spinning in his grave.
Who was Eratosthenes?
He was a Greek scientist who lived in Alexandria over 2,200 years ago and who had successfully measured the curvature of the Earth. He was able to deduce its size with precision.
How did he do it?
It wasn't that complicated. He was in charge of the large library of Alexandria and had read that at Syene, which is now called Aswan, at the time of the summer solstice at solar noon, the sun was reflected at the bottom of a well. Now at his home on the same date of the year, the sun always produced a shadow. At best, the angle of the sun's rays from the vertical formed an angle of 7.2 degrees. If the Earth was flat, the sun, which he knew was very far away, would not make such an angle, so the Earth had to be curved and its size could be deduced by calculating the distance between the two cities. The distance was deduced from the journey time by dromedary, knowing the average speed of the dromedaries.
Oh, that reminds me of my maths problems.
Mathematics is used for that, my treasure.
But how did they get the idea that the Earth could be round? You don't notice it in everyday life.
What do you think? It was enough to go to the seaside and watch the boats in the distance. They could easily see that when a boat was very far away, they could only make out its mast and sails. That was proof that the curvature of the Earth hid the hull. When the boat got closer, they managed to see everything that had been hidden over the horizon.
Wow, that's right. I'll tell Arthur.
You can also tell him that the rounded shape of the Earth is clearly seen during an eclipse of the moon.
What is an eclipse of the moon?
It is when the sun, Earth and moon are aligned. At that time the shadow of the Earth is projected onto the moon and it has a round shape. If it was flat, as some imagined long ago, the shadow would have sometimes given another shape like a line if the Earth had been on its side.
I understand. If it is rounded all the time, it must be a ball.
We could even see by considering the displacement in front of the stars that the moon had to be at least 3 times smaller than the Earth to display such a shadow.
Without having to go there?
And then this idea of a round Earth seemed obvious to the students of Plato's school because for them the sphere was a symbol of harmony and perfection.
Wow.
In this spirit of harmony, they had imagined that the stars in the sky that they saw were encased in spheres, one inside the other. They imagined that the faster they saw a star moving in the sky, the closer they must be to us. They therefore placed the Moon, Mercury, Venus, the Sun, Mars, Jupiter, and Saturn in order.
What about Uranus and Neptune?
They didn't know about them at that time. They needed a telescope to discover them and follow them as they moved across the sky, but they hadn't been invented.
True, they are so far away from the sun. But what is this thing? What does the sun do between Venus and Mars? Shouldn't Earth be there? Why did they put it in the center?
At first, they thought it was like that. They could see the stars, the moon, the sun and the planets spin around us in the sky, and so they imagined that the Earth was in the center.
Well, yes, since we don't feel that we are moving because we are turning slowly.
Well, actually, do you know how fast we are moving right now? At around 1,200 kilometers per hour.
But why don't we feel anything?
In fact, your body is not capable of feeling speed, it only perceives its variation. Imagine you are on a train traveling at 300 kilometers per hour on its rails. You can get up and walk. You can also drink a glass of water without being afraid of the water spilling all over your face, right?
Yes, of course.
On the other hand, if the train brakes, or if it accelerates suddenly, you would feel it. Well, for the Earth it's the same thing except that it never accelerates strongly. And it doesn't brake suddenly. You never feel anything.
So, we only feel it when the speed varies. But why did they never have the idea that the sun could be in the center?
Some did. Like Philaeus of Crotone in 470 BC. He had the idea that everything orbited a central fire, which illuminated the sun, which then turned the light on us. His idea was mainly to add spheres and end up with 10. But later we understood that the sun must be bigger than the earth, and Aristarchus of Samos imagined that it would be more logical to put it in the center. But minds at the time were not yet ready to accept it. But that's not all. They saw over the weeks that the planets sometimes turned back on their paths, like a zigzag or looping. They tried to create a model to anticipate their movements in the future. Eudoxus of Cnidus proposed to add 2 spheres attached to each of the spheres of the planets. It was ingenious but very complicated and ultimately not very precise. Later Ptolemy proposed a simpler model, but that didn't work very well either. It had the planets rotating on a circle attached to another circle centered on the Earth.
Ah, well, it's easier anyway.
That model lasted for almost 14 centuries. We had to wait for Copernicus and his heliocentric model to get closer to the truth.
So, they finally put the sun in the center. But how does this model explain the movement of the planets that go backwards?
This so-called retrograde movement is due to the differences between the orbital speeds of the planets around the Sun. Mercury, being closest to the Sun, is the fastest and takes just 3 months to go around its orbit. Venus, in second position, takes 7.5 months. For Earth it is 1 year. Mars takes 2 years, Jupiter 12 years and Saturn 30 years. Imagine that we are in this blue car and we overtake this red car, which is going slower than us. As we overtake it, we have the impression of seeing it go backwards. Yet it wasn't going backwards, it's just that we were overtaking it. Then, if we take a left turn at the next crossroads, we will see the red car again moving forwards. It is exactly the same for Earth and Mars. As the Earth is closer to the Sun, it has a faster orbital speed than Mars. When we overtake it, we see it turn back compared to the stars.
I understand. And as we take a tighter turn than Mars, we will finally see it resume its normal movement in front of the stars. All is relative.
And it was Galileo who proved that this model was the only one that could describe what he saw through his telescope.
With a telescope we can see the planets orbit around the Sun?
It's not as simple as that. First of all, Galileo observed Jupiter with his telescope. He noticed the presence of 4 moons orbiting the planet. It was proof that not everything orbited around the Earth. Certain small objects could revolve around things larger than themselves. He then observed Venus. According to the model of the epicycles, one should see the planet backlit only. Galileo's drawings of Venus show a big crescent but also a middle-sized quarter and a small full disk of the planet. A big crescent means that it is closer to us than the Sun. A middle-sized quarter when it is at the side of the Sun, and a small full disk when it is beyond the Sun. Sometimes in front, at the side and beyond the Sun. That proves that it revolves around the Sun.
Elementary, my dear Mom. Copernicus was right.
Yes, but his model did not work that well. So, we still kept the model of the epicycles to do the calculations. A little later, Tycho Brahe in Denmark, using an observatory that he had built, made very precise measurements of the movements of the planets in the sky. He was aware that the epicycles were a mistake, but he couldn't help thinking that the Sun was still spinning around the Earth. He imagined a system in which all of the planets revolved around the Sun but not the Earth. This made the Sun revolve around the Earth with a procession of planets around it.
What a funny idea.
A little later, Johannes Kepler used the observations of Mars taken by Tycho Brahe to understand the shape of its orbit and to determine that its movement corresponded to an ellipse, an oval shape where the Sun occupied one of the focal points. This is called Kepler's first law. His genius was to say that if this was the case for Mars, it must also be true for all the other planets.
Is that the case for the others too?
Yes. The Earth almost describes a circle, but Mars deviates a lot from it. There is also Mercury, which is like that. When it spins around the Sun, what do you notice?
Yes, its movement is not well centered on the sun. And it looks like it doesn't always go at the same speed. Look, when it gets closer it accelerates. And, when it is further away it slows down.
Well done! This is called Kepler's second law. And he even found a third law that links the time the planets take to go around the sun and the size of their orbits. A discovery which linked all the planets to each other by his formula. By knowing just one of the distances to the sun we could then deduce the entire size of the solar system.
And did they know the distance of the Earth to the sun?
As you saw, they knew that the moon was about 3 times smaller than the Earth. So, when we saw how big it was in the sky, we knew its distance. And by measuring the time it took the moon to pass from the new moon phase to the first quarter phase, thanks to the right-angled triangle that it formed, they had an estimate, but it wasn't precise enough. They wanted a method that gave precise results without using too many approximations. It is thanks to the theorem of Thales and the passage of Venus in front of the sun that they thought they could work it out.
More maths.
Yes, indeed. Imagine 2 observers who decide to measure the passage of Venus in front of the solar disk.
You would need filters so as not to lose your sight when looking at the sun.
You're right, and they planned for that. But they also planned to place themselves far away from each other on the Earth because this would improve the quality of their measurements. So that way observers could measure the passage of Venus at different places in front of the sun's disk. By precisely measuring the time of the passage they could know precisely where on the solar disk the planet had passed. Then they could estimate the distance from the Earth to the sun thanks to relatively simple geometry. If the angle was small, then Venus had to be closer to the sun. If the angle was larger, it was closer to the Earth.
And what was the use of knowing all this at that time? Space travel?
No. It made it possible to know more precisely the position of the stars in the future.
Yes, to know your horoscope in advance.
More importantly, to know your position when you were lost at sea thanks to bright stars in the sky at dusk by measuring their height on the horizon using a sextant.
Ah yes, all the same, but it's still strange that things like the moon orbit around the Earth without falling on us.
We know the answer thanks to Newton, who asked himself the question of why the apple fell but not the moon when it too had to be attracted to the Earth.
How did he do it?
He considered that the moon must indeed fall, but that its speed and direction mean that it misses the Earth each time.
Well, it only remains for me to tell Arthur that he is wrong.
Will you remember everything I explained to you?
No need. I will say that it would be too bad if all the planets were balls except the Earth.
Well, yes, that works too.